Hello, everyone. Thank you for taking the time to learn about our latest work in the field of microexpression recognition. This work will be published in ICCV 2025 with the paper title Rethinking Keyframe-Based Microexpression Recognition, a robust and accurate framework against keyframe errors, jointly completed by researchers from Beijing University of Posts and Telecommunications and the University of Auckland. First, I will introduce the background related to microexpressions. 1. What is a microexpression? A microexpression is an involuntary, fleeting, and unconscious facial expression that occurs when a person fails to control their facial expressions. It is characterized by short duration, small movement range, and difficulty in suppression. 2. Definition of keyframe. Onset, apex, and offset frames correspond to the start, peak, and end of the muscle movements and microexpressions, MEs, respectively. 3. Definition of action unit. It is an independent movement of a single or a group of facial muscles in the facial action coding system. Human facial expressions can be coded through action units. Next, we would like to ask all of you to complete some simple tasks. First, please try to identify this microexpression. The answer is, this is a microexpression in the surprise category. This type of task is exactly the focus of current microexpression recognition research, and its core is how to accurately recognize microexpressions. Next is the second task. Please try to identify the onset, apex, and offset frames from this microexpression sequence. The corresponding answers are these 3 frames. This task is usually a preliminary step in microexpression recognition, which is used to crop the key microexpression segments as shown in the GIF of the first task. However, this task is very difficult because keyframe index errors are inevitable, whether in machine spotting or manual annotation. Moreover, in current research, the great difficulty in obtaining accurate keyframe locations and the impact of keyframe errors on microexpression recognition are often overlooked. Next, we review the existing methods. The existing methods are mainly divided into 2 categories. The first category is keyframe-based microexpression recognition, which specifically includes 3 forms. 1. Using the apex frame as input. 2. Using the microexpression segment of onset apex as input. 3. Using onset apex offset as input. The second category is video-based microexpression recognition. However, these existing methods all seem to have certain limitations, such as lack of robustness to keyframe errors or accuracy affected by redundant information. So, the goal of our work is to maintain robust and accurate microexpression recognition, both in the absence and presence of keyframe errors. The following is an overview of our proposed framework, CausalNet. Enhancing the robustness against keyframe index errors is a significant focus of CausalNet. As shown in the figure, CausalNet achieves robust microexpression recognition by using the optical flows of onset apex and apex offset to represent the whole microexpression sequence. To mitigate the model's focus on redundant information and maintain accurate microexpression recognition, a causal motion position learning module is proposed. This module learns action unit-related position information through the of direction maps, thereby reducing attention to non-expression areas. In the causal attention block, the spatial temporal causal attention is responsible for information interaction. Meanwhile, based on the causality in the temporal dimension, it generates short-range and long-range feature representations, so as to perceive the overall temporal trend of microexpressions while maintaining sensitivity to local key microexpression information. Causal relation mining enhances causal relationship learning through in-depth information interaction and mining of long-range features. The design idea of the causal motion position learning module is shown in the figure. We first calculate the motion directions from the optical flows separately, and then visualize the of motion directions using different hues. The visualized colors of muscle movements in the action unit regions indicate that the muscle motion directions between the onset apex phase and the apex offset phase are almost completely opposite. This phenomenon shows that muscle movements and microexpressions follow a specific pattern. During the onset apex phase, the muscles are in a contracted state, while during the apex offset phase, the muscles are in a relaxed state. The motion directions of the muscles in these two phases are almost opposite, thus forming a causal relationship. The specific implementation of the causal motion position learning module is as follows. By improving the stable mask, we have designed an absolute positional cross-attention mechanism that is sensitive to absolute positional information. This mechanism uses a sparse attention mechanism for local information interaction and adds pseudo-attention scores to the masked positions of the attention score matrix to encode absolute positional information. The implementation of the causal attention block is as follows. First, the spatial temporal causal attention conducts sparse spatial information interaction, and its mechanism is consistent with that of the absolute positional cross-attention. Then, the module performs causality-based information interaction in the temporal dimension to generate short-range and long-range feature representations. Compared with self-attention, due to the constraint of causality, it ensures that as feature fusion deepens, short-range features only focus on short-range information. In addition, the proposed causal relation mining module deeply explores the association between the contraction and relaxation processes of microexpressions in long-range features through information interaction. We conducted a robust microexpression recognition evaluation under key frames with different levels of errors on a composite dataset consisting of SMIC, CASM2, and SAM. We assume that keyframe errors follow a normal distribution centered on the manually annotated keyframe indexes of the dataset. We set standard deviations of 10, 20, and 30 frames and introduce these errors to the apex, onset, and offset frames in the composite dataset to analyze the performance changes of existing open-source state-of-the-art keyframe-based methods in our CausalNet. In addition to manual error addition, we also employ an apex frame spotting algorithm for apex frame localization to introduce keyframe errors resulting from automatic detection. The experimental results show that our method has better robustness when dealing with keyframe errors. We have listed 3 situations where the apex-based and onset apex-based methods are significantly affected by errors, as shown in the figure. In scenario A, the microexpression information is completely outside the onset apex range, resulting in no muscle information of action unit 4 in the onset apex optical flow. This will have a huge impact on methods based only on the apex frame or the onset apex optical flow. However, CausalNet covers a more comprehensive microexpression motion range, making it more probable to incorporate the peak muscle movement process, and the lost muscle movement information is compensated for in the apex offset optical flow. In scenario B, the erroneous onset frame is too close to the apex frame, so the relative motion between the two frames is not obvious. As a result, the quality of the calculated onset apex optical flow is poor, which in turn affects the onset apex-based microexpression recognition. Nevertheless, the apex-based method and CausalNet both show good robustness in this situation. In scenario C, compared with the ground truth, the erroneous keyframes are shifted backward as a whole, leading to less facial expression information in the apex frame. This has a significant impact on the apex-based microexpression recognition, while the onset apex-based method and CausalNet remain robust in this case. In addition, the situations where CausalNet is more robust to errors than other keyframe-based microexpression recognition methods are not limited to the above 3. The more comprehensive microexpression range input enables CausalNet to have better robustness. Using the annotated keyframe indexes provided by me benchmarks, we compared our method with existing state-of-the-art methods in the 3-class CDE task and the 3-class single dataset evaluation task on MEW. It should be noted that for all datasets, we analyzed the performance by averaging the results over 5 runs. The results demonstrate that CausalNet has achieved a leading position in all metrics on the CASM2, composite, and MEW datasets, and has also performed prominently in some metrics on the SMIC dataset. Thank you again for taking the time to learn about our work. Currently, the code for this research has been open-sourced. If you have any questions, please feel free to contact me via email.